Gotta go fast. Gotta record fast. Gotta be fast because the bread's in the oven, so that will make me go fast. All right, let's get to it. We don't need any more of that. We're going to continue with our analysis of Fourier transformations today. I have another example problem on deck, and this will also help to, I think, clear up some of the what does this mean business. So let's hope that we get 2 for 1 here. All right, getting to it. There is a strong possibility of dad jokes, especially those that are related to frequency. I will try to contain myself. So we looked at spatial functions last time, f of x, and then that mapped onto the spatial frequency k. And that let us say, okay, if I have a function that is distributed over space in some way, what is the frequency content of that function? Does it have more high frequencies or low frequencies or whatever? And we calculated this by applying the transformation that's written here. Basically, you are sampling the function f of x at every value of x weighted by some e to the I business. So with all that in place, then what you do is you say, all right, so now I understand about spatial stuff, but what about things that change in time? We've been doing all of this space and time business lately, so let's look at that. There it is. Okay, so we're going to look at functions of time next. Now, the first thing I want to say about this is the math is exactly the same. We're literally just renaming our variables. The way you think about this conceptually might be a little bit different, but even so, the concepts are almost entirely the same. What I'm basically trying to say here is it's actually not a big deal. It's going to be very, very similar to what we've already looked at. The difference is that we are going to have a time that is measured in seconds or whatever, and then we'll have an angular frequency that is measured in radians per second. And that's just really, business that I hope you're used to at this point. So without further ado, let's get to it. What I want you to think about is, and this is not just like music for the sake of music here, I really encourage people to think about sound when doing this. Because if I'm playing something like this, like there's a lot of high frequencies there. You would expect that whatever that wave looks like in time, the Fourier transform of it is going to have lots of stuff at high values of omega. And if I'm playing down here, there's a lot of low frequency content there. So whatever that wave is that I just played, like you can imagine capturing that signal that is changing with time, calculating its Fourier transform, running it through our integral machine, and then ending up with a result that says, wow, there's a lot of bass in that bass, and there's a lot of treble in that. And this is very meaningful, and it's also useful, not just for signals processing, but yeah, definitely for signals processing. So that's kind of what we're doing here. What I want to start with is an example that probably will make more sense intuitively in terms of the answer. Maybe not the process, but the final result you'll get, you're like, oh, that makes sense. I really hope that's where you land with this. Because the example that we did last time with the Gaussian and all that, like that is neat, and it helps to explain a lot about waves, and it explains things about the quantum world and all that, but it's not maybe as clear in terms of frequencies, how you interpret the meaning of signal and frequency and all that. So this example will be very, it'll be a lot more tangible, I think. And the question is, if we just send in a cosine wave, if we take the Fourier transform of a pure cosine, what does that look like? And this is one that before we do the math, we should actually be able to just draw the answer. I have some function as a function of time, and it's just a cosine, so it just does like this business, just doing the old cosine thing. Well, what are the frequencies in this thing? There's only one, really. There's just, so if this is my period t, then the frequency is 2 pi over t. And that's it. That's kind of the definition of a cosine is it's a wave that is just a constant wave that keeps waving the same way forever and ever, and that frequency never changes. So as a result, the Fourier transform of this thing is just going to be boop 2 pi over t. All of the content is just right there at that point on the axis. It should look like a vertical line, basically. And it's zero everywhere else because there is no other frequency except for that one frequency of the cosine. So that's what the math should tell us. Let's actually do the math and see if that's what comes out of it. All right, calculation time. We feed in our function. Here's our f of t. And omega naught is that 2 pi over the period that I had in the last slide. And we feed it into our Fourier transform integral formula. And the very first thing that I'm doing to do is to make this exponential not an exponential. Because as much as we love integrating exponentials times trig functions is, my feelings about that are, cannot be expressed in polite company. So instead, we're going to turn it into trig functions because then we can use clever trig identities to do the integral. The first thing that we are going to do as a process for processing this integral, sorry, that whatever, is to just take this sum and split it up into two separate integrations. So we'll have an integration of cosine omega naught t times cosine of omega t, and then that will be added to this second term with the cosine and the sine. So we've taken an exponential, split it up using Euler's formula, and then use that to separate the integral into two integrals. Much like with the last problem, it started looking not so bad, and then I made it much worse, and eventually it got better. It's going to get better. There is a strategy here. So looking at the cosine and sine term first, this is where, if you remember a result from the Fourier series stuff, you can deal with this without ever having to do any integration, because you can be like, oh, this is an inner product. I'm integrating. There's some coefficient, whatever. It's just a constant. Don't worry about it. Instead, you look at this and you're like, this is an inner product. It's the inner product of a cosine function with a sine function. And the result from that just has to be zero. Those two functions are orthogonal to each other. Their inner product is zero. Done. No integration required. If you remember that result, you can just, we're already done with half of the problem. Great. So now we have to deal with the other half of the problem, which is this integral of cosine and cosine. And this is where you might be like, okay, so I'm supposed to be clever and I'm supposed to make everything go away and be zero because that's what simplifies these problems. And for the most part, I'm on board with that. There is a little bit of other thinking to be done here, which is, first, let's finish that thought. If the two frequencies are different, if omega naught does not, oh man, that's really unfortunate. If omega naught is unequal to omega, then these two functions will be orthogonal because cosines of different frequencies are orthogonal to each other. But there's one particular case where these two things are not orthogonal, and that's when they are the same thing. Or if, and this is the one that you need to be really careful about, it's a little less obvious. Remember, we are looking at all positive and negative values. We're scanning over the entire number line here. So when you're doing that, what you have to realize is that, oh, cosine is an even function, and that means that cosine of omega t and cosine of negative omega t are the same function. So there are actually two different values that make these cosine terms not cancel out. And those are the two that are listed right here. If the functions are equal, or if they are equal but with the opposite polarity, positive, negative. Well, now what? This is really tricky because you might be like, well, I can integrate this. I have some trig identity that will let me combine these cosines, and then I just integrate cosine, I get sine or whatever. Yeah, I mean, you have, you definitely can manipulate the integrand that way, but you got to look at the bounds of integration. What does it mean to take the sine of infinity? It's some number between -1 and 1, presumably, but that's not really an operation we can evaluate. So are we stuck? No, we're not stuck. We're going to wrap this up because the bread's in the oven and I don't want it to burn. We're going to move on and I'm going to stop trolling and say that yes, there is a function that describes exactly what we need here. It is called the Dirac delta function. I mentioned this a few videos ago. That was really just in preparation for this. So I could say, hey, I said this once before. I said this once before. There is, I'm not sure what's happening here. We're just going to delete all of that. That's probably left over some copy pasta. All right, here's what the Dirac delta function is. Reminder, it is a function that is 0 everywhere except at one particular value where it is infinitely tall. But it is infinitely tall and infinitely narrow such that the product of the tallness and the narrowness, height, yes, height, and width, ah, yes, those are words. The product of the height and width is 1. So the area inside this thing is finite because it is infinitely tall and infinitely narrow in exactly the right proportion. The infinities are the right size. This is the kind of stuff that makes mathematicians go crazy when you say it. I almost said a very different word. Okay. So here's our Dirac delta function. And if I try to plot this thing, so imagine you have a box. I'm just going to do like f x, and then here's x naught. So if this thing has a width of 1 over a, I know that's a weird way to define a width, but then if it has a height of a, then the area inside this box is definitely 1. It's a times 1 over a, the a's cancel out. But what if we take a limit of this function as a goes to infinity? That's going to make this thing get narrower and taller proportionally at the same rate so that the area stays constant. And this is what actually one way of defining and doing calculations with, for that matter, the delta function is to define it as this little step function which has a known width and a known height, and then to take the limit of that function just as is drawn here. So this is one way you can think about it. All right, this was the formula before we left for our little interlude. And now I'm saying, okay, let's express this in terms of delta functions. This will tell us the shape and kind of like the logic of the answer. It's 0 everywhere except at omega equals omega naught, and it will also be non-zero at omega equals negative omega naught. Everywhere else, there will be nothing, but at these 2 points, there will be some value to the function. The pi's here are just for normalization. Don't fuss about that too much. If we had more time for this topic, I would get into more of the quantitative details, but I do want to focus on the idea for this one. So we collect our coefficients, and what we're left with is something that's very similar, to what I drew at the beginning before doing the calculation. What I drew at the beginning was a single spike at omega naught. But what was left out in that initial guess is that there's actually this symmetry here, that there is frequency content, both positive and negative frequencies both contributing to the signal. So this is to say that the Fourier transform of a cosine, which is a pure wave with a single frequency, is in fact a function that just has spikes at that frequency, its positive and its negative version. And that's it. So like that's the answer. We're done. Is this exciting? Yeah, actually, this matters quite a bit. The details of it is going to be the entire next video. That won't be one that is, how do I want to say this? It's not going to be something that shows up directly on the homework, but I think it's a really fun illustration of the physical meaning of all of this math in a way that you can experience with your senses besides just listening to me bab about it. So, babble, yap, gab. I think all of those words just merged. I think I need to stop talking also so I don't burn the bread. So, please look forward to the why it matters demonstration, and I will see you there.